This is our Visionary and Technology seminar. It's our sort of large Jones seminar. That's why we're all here. Thank you for all coming. It's great to see you. And so as part of that, we had a couple of different programs. First, we ran an image contest. So I'm going to announce the winners to the image contest. So hopefully you are here if you submitted an image. Okay. So, well, now you get to see the first place. We always go third place first. Okay, in third place, we have Tian Bao. Are they here? No. Well, congratulations. Can you tell us what you liked about this this image? You didn't know this part was coming.
I didn't know we're going to ad-lib this. It looks like a plane, even though it's not one. So I was into that. Yeah, I thought it was really cool. I like all the different scales. It's bright and shiny, so it's really interesting. It's communicating science but it's also cool to look at. There you go.
It looks like a rocket launch to me.
It really, also that.
Okay.
Topical.
In second place, we have Aaliyah Summers.
Woo!
And Aaliyah is online. Maybe she can wave, but can you tell us what you liked about it?
Yeah, I mean, if you didn't know what this was, you'd think it was like a cool fractal pattern, or maybe it's like fires and smoke plumes, but it's actually subglacial routing of water, which is really, really neat. And so why the ice is flowing where it does has a lot to do with that. And so it's, again, beautiful image, communicating a lot of science, but you could just look at it. You could hang it on your wall and people would be like, interesting image you have here.
Yeah, it's amazing. Great work, Aaliyah. And then our winner for our image contest for the Visionary and Technology series is Hulin King. Yes. The number of memes that this spawned is very large, so can you tell us why you liked this one?
Indeed, again, same theme, right? Communicating science, so it's a micro-scale image, and you're seeing all these really interesting details, and then it also has the adorableness factor on top of it, being a fox. So it was pretty exciting, so I thought it was great.
Yes, well done to all the image participants. They're going to be displayed around during the reception and also in the halls, I think in perpetuity, but I'm not going to be here that long. So, yes, thank you, everyone. Okay, that's not quite yet it for me. I have the great honor of presenting the gifts to you. So if you want to come over here, I will give you the gifts.
I've been receiving gifts such as this yesterday. I got a mug today, so it's the coolest pen anyone's ever been given.
Okay, well, let's start with this one. This is from Simon Pierce.
Oh, thank you.
Yes, you can decide to open it or not. We won't judge.
We'll open it afterwards.
Okay, Simon Pierce is a glass blower in the area. Does really nice work.
So cool. And should we open it actually then?
It's up to you. It's up to you.
But now it sounds even cooler. Now. Okay, see, now you got it. I was like, now I feel guilty for not opening it. How cool! Oh my God, nested wrapping papers. Ooh. All right, we have a tray. Is somebody videotaping this so we can have an unboxing thing?
Yeah.
And I'll be like, she's not really good at it.
Videotaped.
Very cool. Oh, neat. Ah, see? Very, very professional. This is cool. So we've got stuff to set up business cards and things?
That's it. So, okay, so...
Thank you so much.
Of course.
I have cool business cards to put in it. And the ultimate pen can go right here.
It's very professional, and you kind of wonder, why did I come all the way to Dartmouth to get some wood and glass? Yeah. But here, my friend, is the answer.
Okay, so now I open this as well?
Yes, please.
Okay. See, now I had to do that, so I hope this is great. Now we're... Oh, God, this is so much pressure. Oh, my God, it's an Icefin! Oh, how great.
You can open it up.
And it has a pen. It's the C pencil. Ah, how awesome. So did you guys 3D print it?
Yeah, so Lee is in the back in the shop. Kelly's also in the back. This is courtesy of our M shop.
This is amazing.
Amazing design.
What a flex. This is awesome. That's amazing. This is so cool. And now we have Icefin here in our presence. Oh my gosh, this is so cool. Thank you so much. How thoughtful is that? That is amazing.
So when you said that you received a pen in your gift box in the hotel room.
That's why you panicked.
That's why I panicked. How did the wires get crossed about that?
This is so cool. Can Icefin sit there?
So now you now have a beautiful Simon Pierce stand for your Icefin pen holder.
This is incredible. So we call Icefin the sea pencil for some fairly obvious reasons as kind of a joke. That's amazing. Thank you guys so much. That is really cool. I love it. Wow. And it looks remarkably like the sticker. So this is awesome. Thank you.
We'll hear a lot about Icefin in a few minutes.
Yeah.
And so we're honored to have Britney here. She is a visionary in technology. She makes brave choices about the research she does. She was undergrad in Arizona, did a PhD at UCLA, postdoc in Texas, and for a long time was a faculty member at Georgia Tech, and now is a professor at Cornell. She sort of has Carl Sagan's job, so she's probably going to smack me for saying that. But is truly a visionary. She works in now both poles of Earth. She works on asteroids and icy satellites in the outer solar system, and sort of very majestically weaves a narrative about all of the different pieces in her research program. So, without further ado, visionary in technology.
Thank you. Wow. It's kind of hard to live up to that one. Are we seeing it online okay? Hopefully. So we've got an introduction to Icefin. So this is Icefin here in the background. So anyone know where this is who hasn't been there before? I mean, it's kind of in the slide title, but... So this is a particular kind of ice that Icefin's under. So you'll notice there's some light coming through from the surface. So this is Icefin underneath the sea ice outside McMurdo Station in Antarctica, which is where we've done quite a lot of work to develop the vehicle and to try to understand how the ice and the ocean are interacting and how climate change is happening in Antarctica. But the story kind of is really that I got really excited about thinking about ice everywhere that it is, and then I was quote unquote new to the Earth, and tried to figure out a way to study it here on Earth, and that became Icefin. So this is kind of a story about what we'd love to do one day in space and why we're doing it in Antarctica in the meantime. So I really love this quote from Proust that says, "The voyage of discovery consists not in seeking new landscapes, but in having new eyes." And so what we've actually tried to do is develop new ways of seeing things and ways to get to places we've never been able to see before. So actually kind of trying to do both of those. And that's really the stage for Icefin, which is how do you answer a question, how do you explore even is actually part of the question. How do you answer questions you don't yet have even some basic data on? And so that's where we kind of start from this. And so I'm really inspired by thinking about how we solve problems and how we make new observations. And my favorite person in history is Galileo. And so about 415 years ago, Galileo literally built the first new eyes, right? He built the first telescope. And it was basically if you took a pair of binoculars and you cut it in half, one binocular is basically what he built. And what that did is it allowed him to see the universe in a completely new way. And so if you get a chance to read this paper, anyone could read it and have a great time. So his very first paper, it's just like that's a lot to live up to, because he goes, guys, the moon has mountains, there's valleys on things, the moon is a planet, Venus is doing crazy stuff, Mars has got this other stuff going on, galaxies have way more stars than you even thought, the universe doesn't work how we thought it would, and now hold please, because there's some stuff happening at Jupiter. And so what he did is he actually pointed the telescope at Jupiter, and what he could see on different nights was the motion of 4 little points of light around Jupiter, which was just a dot that we'd known about since humans had been looking at the sky, right? There's like 5 to 7 dots they're much brighter and they kind of move in predictable ways, so we knew they were the planets. But this is the first time we saw anything beyond that. And there was no way to explain this because no one had ever thought that there could be something around another planet before. And at the time of Galileo, we thought The conventional wisdom was that the Earth was the center not only of the solar system, but of the universe. And so Galileo says, hold all that stuff about the moon being a planet and galaxies and whatever, because stuff is moving around Jupiter. We have no other way to explain it. But then Copernicus is right. The Earth isn't the center of our solar system. The sun is. Gravity works better. We don't know about gravity yet, but this is how this works, right? All of our observations work better if we move our system around. That didn't get him to be very popular at the time, but in the long run ends up being right and completely shifts how we see ourselves in the universe, which is what science is doing, right? How do we see ourselves on a planet? How do we see ourselves in the universe? And so this 400 years ago is like kind of the first astrobiology, but it's also a person telling us we're not the center of the universe, literally. And so fast forward to the late 90s, and we send Galileo, the spacecraft this time, out to observe the Jovian system. And amongst the things that we discover is this beautiful moon, Jupiter, called Europa. So Europa is about the size of the Earth's moon. So very, very similar in size. It's made actually mostly of rock, but on the outside is about a 30 to 50 kilometer ice shell and a huge ocean underneath. But we didn't know that until we got there with Galileo. We measured its magnetic field. We could see that it had an ocean underneath. But most importantly, or most interestingly enough, this surface looks totally different from everything we've ever seen in the solar system, right? What's missing here? Craters. There's no craters, right? Everything else has craters. There's a few. They're very, very small. But this tells us that Europa is literally tearing its own surface up. And it's doing so over the same time scale as the Earth. So we've got this place, the surface is made of ice. We know there's an ocean down deep underneath it. It's very similar to the Earth in many ways, but this new surface is being reprocessed all the time. And so it really got us thinking about how does this place work and how did we study it? And so I started actually working on the Earth and trying to understand how the ice works to apply to this stuff. How do we figure out how the ice shell is working? Because that's like our geologic battery. Is it moving stuff around? Is it resurfacing itself? Is there life underneath the ocean? How would we figure that out? But you have to start at the surface, and you have to start with these exploration techniques. So that was my original training, and then I got involved with ice-penetrating radar in Antarctica. And that's where we kind of run into the most ice. So we go to the most ice we can find close to us. It's Antarctica. And I originally started thinking about it like a planetary scientist. But this is the most ice we can find. And so Antarctica has up to about 5 kilometers of ice. So we just said Europa is probably 30 kilometers of ice, right? So that's significantly more ice in terms of depth, but it's also the entire planet. So make Antarctica the entire planet, make it 5 times as thick, and that's what we have to figure out. Under most of the continent, there's land, right? It's a continent. There's ice sitting up on top of the rock, but below some of it, there are these things called ice shelves in which the ocean is what's underneath. And so these are really, really large sheets of ice. So Antarctica is larger than the United States. This ice shelf, Ross ice shelf here, is the size of France. That's a huge piece of ice, right? It's made of streaming glaciers that kind of push each other together and create a sheet, and it's floating out over the ocean. So now we're starting to talk about a chunk of ice that's 1,000 meters thick, so kilometer thick, and it's floating on the ocean. This is starting to get to planetarian scale. So that's why I got really interested in that problem. I'll talk to you a lot about Thwaites Glacier, which is going to be more important to us than it is to Europa, but is a part of the story as well. But that's another one of the really big ice shelf systems. About 44% of Antarctica's coastline is made of these ice shelves, these floating remnants of the ice sheet that are out at the boundaries. And they used to exist in Greenland, but most of them have collapsed. 100 years ago, there were all kinds of these in Greenland. They don't exist anymore. And then most recently, we've gone out to Fimbolisen, which is a smaller ice shelf on the other side of the continent. So we're trying to go and explore these places for both Earth and for planetary reasons. So that's how I got involved in studying Antarctica. But the reason everyone in here should care about Antarctica, even if you don't care about space, is kind of summarized here in this image. Anyone know who this is? No, the glaciologist will. But this is Thwaites Glacier. If you've heard of a glacier recently, it's probably this one, because it got nicknamed the Doomsday Glacier. But it's a really interesting system, and it is the place where the largest single campaign to understand a single system in Antarctica took place. And it just wrapped up, basically. It was supposed to be a 5-year program that turned into an 8-year program. Thank you, COVID. And so what happened was the British system, the National Environmental Research Council, and the United States National Science Foundation, as well as the Koreans and a few others, have mostly this collaboration was between NERC and NSF. And we wanted to go out to this glacier, and it's a huge international team, the most time and money ever spent on trying to understand something. And you can see why, right? Is that an ice shelf? What does that look like? It's falling apart, right? This is a currently connected system of icebergs. It's no longer what we think of as an ice shelf. So we went out to this location, which I'll talk about in a moment, which was the closest we could get to a really important part of it. But this is what you can see. So in the last several years, you can actually watch the entire ice shelf just break up. So here we have this massive chunk of ice that's actually kind of holding the ocean from getting inland in Antarctica, and it's breaking up really, really rapidly. And so this ice shelf is falling apart, and it's really, really an important one. And the reason it's important to study this is because in systems like Thwaites, what's happening is this grounding line, the place where the ice is meeting the ocean and the seafloor for the first time, is being melted back. And so as that melts backward, it makes the whole system more unstable. It can allow thicker ice to be now in the ocean, and so then it retreats back and it flows faster. So you get feedbacks between how much ice you're losing and how fast the ice is flowing. And then in the case of Thwaites, because it's also extremely warm and it's in this really interesting place, it is incredibly unstable and it's starting to fall apart. And it's protecting a large portion of the coastline. And why this matters is that the entire system that Thwaites is actually holding back, that's keeping this ice up on the continent of Antarctica, represents somewhere between 1 and 3 meters of sea level rise. And so this is just a picture of what things look like in San Francisco after a little bit more than 1 meter of sea level rise, right? If we looked at this for New York, you start to lose like Rockaway Beach. So we can really change the coastline and really human civilization because of these things like sea level rise. And so why does it matter when we start thinking about losing this ice that's so far away from us? It's because it really is going to affect humans. And this is a very United States perspective, right? So this is San Francisco. But there are places that are within feet of sea level rise, entire countries, island nations, and things like that. So as we start to just slightly change the sea level, it's hugely, hugely displacing people. And so we have to really think about that and how to measure it and how to get better at predicting it. So space, climate, what's happening under the ice, they're actually weirdly the same question, and we needed new ways to measure it. And so that's how I entered the story. I got really interested in grounding lines, and I really wanted to be able to get through 30 kilometers of ice one day on Europa. And so Icefin is the robot that our team has been building for a number of years, so starting in 2013, but the ideas for which kind of started before that. And we built it to go to Antarctica. So back to that first opening slide, this is a really fun picture, and the reason it's really fun is that we just happened to be doing some testing when the divers were down underneath the sea ice. So the picture I had shown you before is like a picture we took through the ob tube, which is like this tube, they sit in the ice and you can like climb down in it and see underneath the sea ice. And we like took a picture through the window of Icefin. This one is where the diver, like the scuba divers, are actually under the vehicle taking a picture of it. So it's really kind of fun. But you can see what Icefin's doing here. So up front, we have all the sensors that are measuring the ocean. So we put them up front so that the robot hasn't disturbed the ocean before we get to measure it. And so up front, we're doing things like measuring the temperature and measuring the salinity of the water column. We're measuring oxygen. These 3 measurements give us a fingerprint of the water column. They tell us how much melting has happened, where the water came from, where it's going, and we can match it up with the speeds of it and try to figure out what's going on underneath the ice. We have cameras, we have sonars, we have cameras because we're humans and we like to use our eyes, and that really helps us. But we have sonars because we're never, there's not a lot of light down there, and we don't see anything until we're very, very close. And a whole bunch of other science sensors. So this is the whole robot. So this is in its current configuration. So that red sensor is our CTD, so the conductivity, temperature, and then you add that to the depth of the robot, and that tells us all about the ocean. The oxygen content tells us how much melted glacier water there is in it, or how much glacial water or subglacial water is coming out. So inside the vehicle, we actually have 7 modules. So the front is kind of this forward-facing science and risk. Right behind that is a thruster module, and there's a matching one in the back. And those are our directional thrusters. Inside the middle piece is all of the controls hardware. So we've got batteries, we have all of our controls and communications, and our basically monitoring the whole robot. Right in front of the electronics and in the back of the electronics are swappable science bays. The one right behind it allows us to measure how fast we're going. So it's a Doppler velocity logger, right? So that's kind of telling us how fast we're going. And when we put it with a sensor inside the vehicle that's giving us orientation, that's actually how we get navigation. We start at a place, right? We know where we are exactly. We know how fast we've been moving in what orientation. And so we can navigate that way under the ice. And so then this module here is kind of fun because we can actually swap it. We can point it towards the ice, we can point it towards the seafloor, and we can switch out all of the instrumentation. We can also point this module towards the ice or towards the seafloor and swap out the instrumentation. So it allows us to do lots and lots of different science with the same vehicle. So that's kind of what it looks like, just in a frozen image. So the yellow material here, and you can see it there in the model, is syntactic foam. So it's basically high pressure tolerant foam. So that allows us to float, right? So we have to float neutral in the water column, so it's salt water. So we have to make something made of aluminum and a whole bunch of batteries float neutrally. And so all that yellow stuff is the foam. And we have cameras front and back. Backup cameras are awesome, especially if you have a tether. So we have a really long fiber optic tether that has a jacket around it that allows us to actually pick up the vehicle with this little tiny fiber optic tether. It's terrifying, and I hate every minute of it. But it allows us to communicate with the vehicle the whole time and actually manipulate it under the ice. And if we lose the robot, we get all the data back, right, which is the whole point to begin with. So that's kind of what we do. And we can manage all of those things. So that's Icefin. So we've been all over the place. So this is Icefin doing her job under the ice. Kind of turns around. It has what we call 5 degrees of freedom, which means we can turn, we can pitch, we can go forward and backwards. We don't control roll. We put a whole bunch of heavy stuff on the bottom and hope it doesn't roll over. And so far, we're pretty good at that. We weren't as good at that all the time. But you learn, right? So you engineer, you get better at things. It's really hard to do in something that's that narrow. So Icefin's almost 4 meters long, so 13 feet long, but it's only about 9¼ inches across. And the reason for that is because the fatter the vehicle, the bigger the hole you have to melt through the ice. If you're going through 4 meters of sea ice, like right out here, we can just drill through it really fast. But if you're trying to go through 1 kilometer of ice, that's a whole bunch of fuel you have to use to make really, really giant holes in the ice. And so the skinnier we can make the robot, which makes our lives much, much harder, the better it is for fuel use and the more easy it is to take it in crazy places. And all of those pieces come apart so that we can pack it in small places and take it out into the field, which makes it a lot easier to use. So we're going to talk about Antarctica and robots. That's what 4 meters of ice looks like. That's one of the drills I mentioned that we can use to get through the ice, and that's Justin and Peter, looking very cheesy, because they've just put this hole through the ice. So we'll launch the vehicle through a frame like that. So we actually put it on what we call the LARS. So this is our launch and recovery system. We lay it on this metal frame, and we actually, like rocket style, like tip it up and then launch it downward, so opposite direction. And go through the ice that way. So here we are working on the sea ice outside of McMurdo Station. So there's Enrica and Andy, and Ben is up at the top. So it's a whole group of people that get to work on it. Here we are. It's got floats on the back. We're installing extremely important electrical tape to make sure things are working well. Any port in a storm. I love these because these are some of the Icefinsicles. So this is Icefin heading down, Icefin after it's come back. You can see the icicles kind of formed on the front of the vehicle. What does it look like for us to set up? So this might be a semi-typical day. Here we are driving out in our various vehicles, building the whole frame, building the robot up. We live in this tent, live and operate out of these tents. Then we pick the vehicle up once it's built, launch it, put it down through the ice, vehicle perspective on how to go. And that's outside of Erebus Glacier in Antarctica. So that's what our day looks like. On a normal day like that, if we're doing sea ice operations, it takes us 3 hours probably before we even start, and then maybe 7 or 8 hours when we're in the ice. This is what it looks like to operate it. So this is inside a different place, but these are 4 different camera views. So we've got our rear view camera, as I mentioned, we're monitoring the tether. Forward camera is up in the front, and then this is our HD camera, which can be pointed up at the ice or down at the seafloor, depending on what we're doing. So we've got visibility in every direction. So this is our former software engineer, Anthony, at the controls desk. There's Matt and Andy and Ben also doing controls. Oh, I don't have the video of me, or the picture of me there. It's a really cheesy picture. So this isn't a really up-to-date version. We have a new version of this, but this is what our mission looks like. So we have the position of the vehicle here on a map of McMurdo Sound, and what we're doing here is we're actually mapping this rift in the McMurdo ice shelf. So while we're going along, we're looking at the sonar feed. That's actually most of how we're navigating. So we've got a sonar feed out the front of the vehicle, so you're seeing the structure at the bottom of this rift in the ice shelf that we're mapping along. But the whole time, we're also seeing feeds on which direction the vehicle is pointed. So this is our heading here, our depth and our altitude, so our position relative to the ice or to the seafloor. We've got all of the efforts of the thrusters here, heading, temperatures of various parts, some of our science sensors, so we can be looking at the health of the vehicle and the systems the whole time that we're driving. So we can do this with as few as 3 people, but it's really, really hard with that number of people. 6 is definitely better, because there's just way too many sensors to be able to monitor well if you're just a couple of people. So here's a few pictures of us deploying it. So this is actually out at Thwaites Glacier, which is the one I mentioned, the Doomsday Glacier. But this is Andy and I. Dan is inside the tent monitoring the vehicle health as we're getting ready to put it down under Thwaites. And so this is 600 meters of ice that we're dangling the robot off of this fiber optic tether. So here's that yellow is the fiber optic tether right there. This is a fun picture. I'll show you the video from the vehicle later, but this is as the robot's heading down for its first dive at Thwaites. So I'm actually driving the robot, though not yet. So you're seeing up the hole, down the hole from the front of the vehicle, and one of the cameras is turned off. So that's kind of fun. And then this one, you'll actually see the video from. You can see this is actually us making it to the grounding line of this glacier. So this is the ice sitting on the seafloor. So this is like our walking on the moon picture, I guess, of the coolest thing we've done, for sure. So that's kind of fun. And you'll notice, if you're a video game person, a little PlayStation controller here, that's literally how we drive this thing. And so we're getting feeds all the time, and Dan and I, or Francis and I, are talking the whole time. And this is what you really want to see, which is your entire research program coming back to the surface of the ice after such a dive. And most of the time, that has happened, which has been great. So this is pulling Icefin back after its last dive. So we did five total dives, 6 missions, one in which we got ourselves stuck and came right back up after 6 hours of getting it out. But that's how it works. So anyway, so it's kind of a lot. So now what I'm going to show you is back to this climate story. So what are we doing with the robot here on Earth, right? We know what we want to do one day, which is figure out how to get through ice, figure out how to explore it, understand the science there too. But in the meantime, what are we doing here? And so this is this International Thwaites Glacier collaboration. So this is our team before we left for the deep field. So that's Icefin in the middle, and our colleagues from the British Antarctic Survey, from NYU, and actually we were joined by folks from Penn State that weren't there at the time of this photo. But that's just the part of the team that we actually worked with. There's 9 projects in ITGC. So ours, the MELT project, is only one of 9 projects. I know Mathieu is involved in several as well. So anyway, so this is our work here on going out to see Thwaites. So there's all of us now out in the field. As I mentioned, we were joined by our colleagues from Penn State, and then we've got actually some BBC reporters that were there for a while. Interesting process, and some of our field techs from Bass as well, and David Vaughn, major force. So what do we do with Icefin? There you go, Jacob. So this is a terrible video of how we do the science, right? So we deploy Icefin through the ice. In this case, at Thwaites, it's 600 meters. So we go dangling ourselves through 600 meters of ice, come out through the bottom, turn on all of our sensors. We drop a weight And then we go forward, trying to map everything that's happening. And so that's where this data set that I'll show you here in a moment comes from, is from having all these sensors on as we swim out underneath the ice. And this is the video. So I showed you the picture of the grounding line where you see the sonar reflection that's saying the ice is sitting on the seafloor, and we're all excited. This is the video actually from that point. And what you're going to see is the ice doesn't really look like ice, right? So this is actually ice that's full of sediment that's been picked up because it's been scraping along the bottom of Antarctica, picking stuff up. And this is right when we get to the grounding line. We just basically couldn't fit the robot any further back. So the ice, so Icefin's 10 inches, the ice, the volume here is, it's maybe 20 inches or less tall. So we couldn't fit Icefin over the rock in front of us at that point in time, to go even further. But what you're seeing here is the organization of all that sediment by the flowing ice. And you're also starting to see that the ice is kind of scraped into these really interesting shapes. And that story is really important because that's some of the observations that we made, is how quickly the topography of the ice is changing because of melting in this environment. One of the crazy things you could do is you could see in that video, you could see streams of particles coming out of different parts of the ice, right? You could see the rocks falling out. You could see drop stones that are about to happen. And that's your eyes. You're using them as a temperature sensor. So this ice is now melting, right? So you can see it with your eyes. So now back to that picture, so you know how Icefin's going, and it flows all the way back to the grounding line. This is from two different transects. So here's where we put the hole, is this yellow dot here. The red is us driving in this direction. We ran out of tether. We got so close. It's like 100 meters that way. We have 3.5 kilometers of tether, and we ran out of it. So I was like, no! And so then we made a little bit of a left turn on the next one, and we made it. So we made it to the grounding line there, so that was really pretty exciting. What do all these different colors mean? So that gray stuff there, that is actually measuring the topography of the ice. So we've got an altimeter on Icefin that's pinging up at the ice as we're swimming along. And we've got a DVL, or Doppler velocity logger, that's also measuring current, but also pings off the seafloor. And we also have a sonar, which I won't show you the bathymetric sonar, but we're mapping the sonar as well. So the ice topography is real. So this is the topography measured by the altimeter on the vehicle. The seafloor topography is also real. It's the real seafloor topography measured by the vehicle. These are little colored points for the glaciologists in the room. This is a former potential grounding line position. This is the one that is the strongest evidence. There's another one that might have been here. But this is the really best one that we found. And so we actually know where this glacier was sitting at one point in time. And this one is probably about 12 or between 10 and 12 years before we took this data. So it's also, this grounding line's moved back really, really far in that time as well. So we get to take a look at all of that. And then the most important thing here is actually that color in the background. What this is colored for is kind of temperature, but here it's called, it's basically how much heat is in the water column. So what we've done is, water, the melting point of ice changes as you put pressure under it, right? So what it's done here is that those colors mean how much above its freezing point is the water. And so you'll notice these are many degrees, right? More than 2 degrees above the melting point of the ice. For most of Antarctica, it's within 1/4 of a degree. This is 2 1/4 degrees. This is a huge amount of heat. And so this is why Thwaites looks like that. We're not that surprised to find that. We expected to find that. What's more interesting is what's happening when you get up to the top. We also didn't expect the ice to look flat. We super didn't expect it to have all these staircases. The crevasses are super strange. And the topography changes from right after it made it into the ocean to downstream, where it becomes really, really staircased. This all is important because it's actually telling us about how the melting is happening, at least in this region. And so all of that's kind of new. But you can also see that there's a lot fresher, it turns out, and a lot cooler water right up close to the ice. Why is that? Anyone think about it? It's fresh water from melting the glacier, right? So you're melting ice from the bottom of the glacier, and then that fresher water actually sticks up closer to the top. And so it's not able to flush out entirely. So it's actually not thinning as much as we thought it was going to thin, or as fast as we thought it would thin, which is kind of interesting. It's still melting, and there's still an absolute ton of heat, and a ton of melting happening. There's a lot happening. It just was less than we expected, but if you think about it, we probably should have known that. So it's interesting. Part of the story is this. So I mentioned you can start to see right in that grounding line picture the shape of the ice. Right? It's kind of rounded, and it actually matches at this point in time. If you looked at the shape of the seafloor, it's kind of folded, and it looks kind of like the ice here. So the ice and the seafloor look very, very similar. When we move downstream, right, you can start to see that there's some shapes forming. This is that still where you can see this particles flying out of the ice. We can start to see that now it's got this kind of rippled, almost straight up and down thing happening. It's called a terrace. But then we get further downstream, and the terraces start to look like this. So we've got a flat top, and we've got like a 10-meter wall that's almost straight up and down. And that's not what we see right at the grounding line. So this thing's crazy. There's a fish. Those scallops that you're seeing, those kind of round pockmarks, those actually tell us about how the melting is happening. And it's happening very quickly and very turbulently when you see these pockmarks. The flat stuff at the top and the bottom is more surprising. We don't see that in other parts, and you can see just how flat this is. And what it's actually telling us about is the rate at which and the process by which this is melting. In these flat areas, it's being suppressed by this fresh water, and so it's a molecular process. Heat's moving slower in and out of that layer. But at the walls of this terrace, it's going really, really fast. And so the topography all over is crazy. I'll show you more why that means in a moment, but one of the coolest things that we got to see has very little to do with climate change, but it was really, really fun, so you have to take a look at this. First of all, here's more weird ice. So what you're about to see is ice that looks completely different. This is almost completely clear with very, very finely or carefully sorted pebbles. Not a lot of sediment, but pebbles in this very large crystalline ice. It's possible this is a frozen-on subglacial lake or something, but weirder are our little friends right here. So we just happened to come up at the right place to see these absurd little creatures. These are ice burrowing anemones. And so you can see here's this like space field of sorted particles in the ice, and those little legs that are sticking down are anemones. So this is a type of an anemone called an Edwardsiella, and they're normally burrowing into the ground, and they look like this, and they'd be like, you'd be scuba diving around, you'd see them kind of like come talk to you. Those are the ones sticking out of the ice. And so there's all these little guys everywhere, and if you caught it right back here, if we back up a little bit, you'll be able to see, I mean, these are kind of aliens, right? These are like aliens on our own planet. So I start thinking about Europa, like, how is that not a thing, right? So here's one actually up inside its burrow. You can, in the stills, you can actually even see its eyes. It's really crazy. So these things are burrowing into the ice, and they're hanging out, and they're filter feeding, and they're getting energy. And they are like 15 kilometers or so from the front of the ice. So it's not direct, it's ocean water for sure, but they're really pretty far from the front, and they're crazy. So really wild place to be for a lot of reasons. So we've got this whole world under the ice. The ice works differently. Here's rocks that are about to fall out of here, right? You guys live in an area that was just tormented by ice sheets, right? So you've seen, right, we're surrounded by drumlins. All the topography of this area, of the area around Cornell, has all been sculpted by ice. And you've probably seen drop stones, right? Stones that make no geologic sense where they suddenly are found. Well, this is one that's about to make no sense sometime later when someone finds it under thwaites. So this is a rock that's actually been peeled along from the bottom of Antarctica somewhere and is about to melt out and drop in the bottom. I love that one. And this is that terrace that's forming very close to the grounding line, right? One of these first little ones that we saw. So this is all wild. It's a wild place to be. We could see that there's differences in the melting, so this is another way of looking at it. So one science graph or another science graph. And this is actually a zoom in of us actually coming up close to the side of a crevasse. And what you can see is the wall of the crevasse is melting out kind of like the terrace that I showed you earlier. So in these places, we're seeing these really vertical faces that are melting really differently, right? The flat parts are very, very flat, and the steep sides are very, very pockmarked, right? That golf ball texture. And it's kind of telling us about how the ice is melting, right? So we've got flat stuff and this really, really steep stuff, and it really matters. It's actually telling us about rates. So if we go in and we take all the measurements, the temperature, the shape of the ice, the current speed, and all of that, we can make a parameterization of how fast it's melting. And what it's telling us is that the bottom of the ice is melting around 5 to 10 meters a year, which is much faster than other places in Antarctica, but is way less than we thought it would be, given how fast we're losing the ice at Thwaites. But what's interesting is that the crevasses are melting much faster, at least an order of magnitude, perhaps even more. And so actually the weak spots in the glacier are being melted out very, very fast. And so this story of Thwaites falling apart at its seams also is partially the ocean doing that. So there's a feedback between how the ice works, how it's bending and breaking, warm water getting up inside of it and further destabilizing this. And none of that was really known or ever observed because we'd never had anything inside a crevasse or under a grounding line or in a place that was this warm before in Antarctica. So all of that together really helps us to figure out how all of this is working. I mentioned in the abstract that we were doing lots of these things. So Thwaites is the one that gets all the attention. It's crazy and it's way out of balance. And it's because it's going to affect us all soon and right now, right? Greenland is accelerating its contribution to sea level rise. So is Antarctica, but Antarctica is going to grow faster over the next 100, 200 years. So right now we're most affected by mountain glaciers in Greenland. We're going to, in the future, be the most affected by Antarctica. So we got to think about it. But we have to also look at the parts of Antarctica that are not falling apart at the seams so that we know what a healthy-ish glacier looks like. This is a super weird system that we went out with our New Zealand colleagues at the exact same time, basically, well, 2 weeks before we took the data that I showed you from Thwaites. We had the other robot out at the other side of the Ross ice shelf. So that big ice shelf I showed you at the beginning, that was the kind of inspiration for a lot of our work. So this is a much colder, much different place. So here's that same kind of data. So Icefin went down through the hole here, and then drove towards the grounding line and away from the grounding line, and then we actually explored a crevasse for the first time here. And what you notice is, remember I told you, so this is actually total temperature, but the heat here is actually only, here is kind of colored for how much heat is in the water. So this is a place where we have 0.25 degrees of total heating difference, right? 2.25 degrees at Thwaites, 0.25 in the whole column here. This is also about 600 meters of ice, but it's in a place that's much, much colder. And so it's at the back of the Ross ice shelf, about 1,000 kilometers from the open ocean. And what we can see is much more what we expect. There's a little bit warmer water where it's just barely above melting point that's coming in. It's being flushed a little bit with meltwater from the glacier. And this glacier in this place is actually not even moving. It's a super weird place where this glacier is kind of stuck for the moment. And then we went up inside of this crevasse and got to explore some of that. So what you'll see is that there's some melting, right? We can see those same textures that we saw at Thwaites, but nowhere is it flat. So that molecular process is not happening here. The stratification isn't very important here. We have melting from this scale to this scale to this scale to this scale, but it's all pretty much the same, even on the bottom and the sides, right? So it's melting the same rate everywhere. At the seafloor, this is actually kind of the history. So this is former crevasses that were on the seafloor. So back when this ice stream, before it stretched up, it was sitting on the seafloor. And so we actually have imprints of these crevasses on the seafloor from before they lifted up. So about 100 years or so of history there. So it's all this different kinds of ice, different seafloor structures. And then we actually kind of took Icefin up inside of the crevasse. And one of the cool things about it here, and we saw some of this stuff at Krell yesterday, is that this is the first video of actual marine ice being formed. So marine ice forms when we're very close to the freezing point. So some places this glacier is melting, and inside the crevasse at the very, very top, it gets cold enough that you can start to create new ice. And that new ice is actually forming out of the ocean. So you see here, all of a sudden the ice is kind of green and kind of weird shaped and a strange texture. So this is slowly growing, salty-ish ice. It's mostly fresh water, but it has a little bit of the material from the ocean stuck up inside of it. So this is actually really interesting for both just understanding how glaciers work and how freezing works, but also fast forward to Europa and everything Jacob's group does, right? Which is, how does salt get in the ice? How quickly does it do that? It'll affect everything about a planet. And for something like Europa, This is how we built the ice shell entirely. We slowly grew the ice shell out of the ocean, and we've been thinning it and thickening it over time. So this is a really cool, fun paper, and we did more work on the crevasses. We've kept working. So I mentioned Fimbalisen, which is kind of in the middle. So Ross is super, super huge and cold. Thwaites is super huge and going crazy and breaking up. Thimble is kind of like in the middle, where sometimes it's melting quickly in some places and only some parts of the season, and most of the time it's fairly cold. So this last season we were out with our Norwegian colleagues and our British colleagues and Icefin again, putting Icefin. So this is dive 1. This is significantly less stressed later at the end of dive 3, putting Icefin underneath it. I just wanted to show it because this is a totally crazy environment, and I mentioned it to a couple people in passing. So this is a channel that's being melted into the bottom. So the ice is about 425 meters thick, and it's basically flat at the top, and this is a channel that the ocean is carving underneath it. And one of the fun things is this is now looking up. So this is the HD camera looking up at the top of the channel, and we're crossing over it. And what you're seeing is almost like dunes, except it's dunes of melting. So the melt has made these interesting, very long-scale melt structures. So it's not actually crystals, but it's almost forming these dunes along this axis of the channel. So it's really interesting, totally different regime. So we need to understand all of these processes to really know what's going on under the ice. And so it's been really fun to take Icefin, to have new eyes, see all these weird places, and try to take all the data together to allow us to figure all of this out. And so some things for the glaciologists and the climate folks, right, is that we really see these different regimes being important. We've only been to places that have relatively slow ocean flow, and I'm very suspicious that really fast flow changes the system I just described at Thwaites. So further down the coastline, which is also affecting sea level rise, are these two other ice shelves in which the topography is different and the speed of the current underneath is different. But all of this is really three-dimensional, and it really matters. And so how important salt is, how important buoyancy is, how important current speed is, and how important or the shape of the ice topography all interacts with each other. And the fractures in the ice dynamics interact with the ocean. And right now we draw two-dimensional pictures, and so we've got a lot more to do. So I think there's a lot of comparisons we can do to maybe help make all of this better. And so then that's what we're trying to do, right? Is think about how do you measure any of this to begin with? We should start here. We know how ice is going to melt and freeze. We're going to figure this all out. But back to Europa, what do we want to do? Well, I showed you up at the top of the crevasse how we think the ice shell is forming, right? So Jacob and his group are doing experiments on how much ice gets, or how much salt gets up into the ice. All of those cracks you see on the surface of Europa are full of salt. Probably because there's salt in the ice, right? So it's getting broken down in weird ways. There's folks here working on how that affects the mechanics of the ice, right? You've got Krell that's doing all this crazy work on how ice bends and stresses over huge scales potentially. So all of these things are really needed to start figuring out the ultimate ice shelf, which is Europa. What are we doing? So we built this guy to kind of teach us about how to explore places we've never been and how to ask these questions. But we also just recently sent this guy to space. This is really fun because this is the first talk I've given since we launched Europa Clipper. So it launched just a couple weeks ago. A few of us were out for the launch. It's the wildest thing. So it's a spacecraft going out to be the successor to Galileo, and it will focus entirely on Europa. And so what we're going to do is we're going to orbit Jupiter, and we're going to go and make about 50 close flybys of Europa. All of the information we have about Europa came from 6 close-ish flybys of Galileo. So imagine what we can do with 50 and the right instruments, and on top of that, most importantly, at least to me, this antenna here that says reason, that is an ice-penetrating radar. It's the way we study ice in Antarctica. It's how we see the climate history. It's how we see the base of the ice, how it's changing, how the ice is breaking and flowing and all of that. And we're going to send it to the ultimate ice shelf. So I'm super pumped for that. And we have just 6 years now to wait for it to get to Jupiter. So hang on. So some people will be in college at that moment, and I'll hopefully still be teaching at one. Yeah, so we're going to go and actually do some of this stuff. So the lessons that we learn about how the ice works here on Earth hopefully help make our planet better, but also help teach us about this weird place that Galileo taught us about a long time ago. So this is like our first, this is our team in 2018. With Icefin, it's my favorite picture of us. But I also just have to point out that in that picture is a scientist who was never formally trained as an engineer, that would be me, but who's worked on spacecraft and how to build those forever. There's a PhD student in robotics, a PhD student in geology who also has a degree in biology and in finance, because he's weird. There's a master's degree student in computer science, a master's degree student in electrical engineering, a former undergrad who is still the lead engineer who built the first Icefin with me as an undergrad, who's a mechanical engineer, Andy, who built a bunch of instruments, including a microscope and a water sampler, Tegan, who's a seismologist. So all of those people from all kinds of different backgrounds were needed to do all this stuff. And so when we talk about technology and robotics and how to save stuff and help people, it takes all those kinds of people. And so it's not an engineer or a scientist or anything, it's everybody. And it's a really human endeavor. And so it's been really cool to be part of that. I used to get to say, oh, I'm the oldest person on my team and I'm only 30. I'm no longer that age. I'm 42, but that's still pretty young, which is kind of fun. But there's many things that all those people will go and do, and the people that are working with us now. And actually, Francis, so Matt's still on our team, and Francis is now our kind of lead robotics engineer on our program. So started as a PhD student, built a whole bunch of systems we think we'll send to Europa one day, but now as an engineer, so as a team engineer. So anyway, so I'll leave up some weird videos of ice doing strange things from Thwaites, and take any questions that you might have.